Okay, welcome everyone to Physics 203 Class 17. This will be on infinite square wells, which will be the first system that we apply our um, independent, time-independent Schrodinger equation to. This is a very common system where we have confined particles confined to a limited space. And we'll see a couple of themes emerge in this uh, application. The first is that what are called the boundary conditions to the problem, lead to the quantization. Um, Quantization meaning the discrete, separate energy levels that are characteristic of quantum systems. And also, we'll see that the infinite square well obeys the um, Bohr's correspondence principle, which we talked about several videos ago, and which states that uh, class quantum physics should merge smoothly into classical physics as we take an appropriate limit to large systems. Um, okay, so infinite square wells. So first, setting up a calculation using the TISE, or time-independent Schrodinger equation. And we're going to be looking at the potential energy and the boundary conditions principally here. So here is the one-dimensional infinite square well, also known as the one-dimensional box previously. Its potential energy is from 0 to L, meaning the particle experiences no force in that region, and then jumps up to infinity at 0 and infinity at L, meaning the particle cannot, it's an infinite barrier, and the particle has no chance of getting outside of the well greater than L, to positions greater than L or less than 0. And this is the good old time-independent Schrodinger equation, um, which is a differential equation involving um, it doesn't have the time derivative, which is why it's called time independent, but it's a second order, meaning a second derivative of the wave function with respect to x, um, plus which is really the kinetic energy term, plus the potential energy times the wave function is equal to the total energy times the wave function. So before, we looked at this system and we assumed that there would be wave-like solutions because as particles act as de Broglie waves, but that was an approximate treatment. Now we'll show that these sine wave solutions, which we assumed before, several videos ago, actually come out of the solution of this time-independent Schrodinger equation. Okay, so how do we go about breaking this down? Well, inside the well, V is equal to 0. So this equation simplifies. This term will disappear here. And then after rearranging, multiplying by 2m and dividing by h bar squared, and um, solving for the second derivative here, this becomes the second derivative of psi with respect to x squared is equal to, remember this term here, v of x is gone, is just equal to minus 2me over h bar squared times psi. And that's a little bit of an awkward combination. So we just rename it minus k squared times psi. And k is suggestively named because it turns out to be the wave number of the wave function. So k would be equal to, since k squared is 2me over h bar squared, k would be the square root of that, or square root of 2me over h bar. All right, so what we have here then is a differential, this is a differential equation, but we've simplified it to a more manageable differential equation for the wave function psi of x. A differential equation as you probably realize, but it bears repeating, is it's an equation whose solution is an entire function. Okay, so it's normal equations, we solve them and we get a single number. Differential equations, we solve them and we get a whole function. So we're looking for a whole function, psi of x, which when differentiated twice gives back minus k squared times that function again. And so two functions which are flipped negatively after to the negative after two derivatives are the sine and the cosine. The derivative of sine is cosine, and the derivative of cosine is negative sine. So if you take two derivatives of sine, you get minus sine. If cosine, the derivative is minus sine, and you take the derivative of minus sine, you get minus cosine. So again, the second derivative of cosine is minus cosine. So that's promising because we have here the second derivative of the function is supposed to be minus the function times some constant k squared. So with that, all that in mind, we try out the solution, a combination of some constant times sine of k times x plus a constant, another constant times cosine of k of x. And you can verify that if you take the second derivative of this function, you will get back, because each time you take a derivative, you pull out, by the chain rule, you pull out a k here in front, you will get minus k squared times this right-hand side back again. Okay, so we found a solution for the function. And now we impose what are called boundary conditions. Okay, very important to all differential equations, boundary conditions. Here the boundary conditions are, we know that the particle cannot be exist to the left of the infinite square well because it's restricted by this infinite wall here. So the wave function must go to 0 at x equals 0. So since psi of 0 equals 0, if we look at this, if we plug in 0 for x, sine of 0 is 0, so that would be fine. But cosine of 0 is 1, so we would have, this would become plus b. So in order for psi of 0 to be 0, b must be equal to 0. So that's an example of a boundary condition restricting the possible functions which will solve our equation, our differential equation. So we must have b equals 0. And then the other boundary condition is psi of L, psi at position L is equal to 0. And for that, we know that we only have the sine term left, but that has to go to 0. And for that to go to 0, we must have k times x equals L. So k times L must be a multiple of pi, n times pi, because sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, etc. So we have this second boundary condition, psi of L is equal to 0 at the right-hand side, tells us that KL is equal to n pi, or equivalently k is equal to n pi over L. Okay? So as I said, boundary conditions, not only in quantum physics, but in any case you run into differential equations, they always act to restrict your possible solutions, as they have here. So here, because b is equal to 0 and k must be n pi over L, we get psi indexed by this integer n. We know that n has to be an integer, would be equal to a times the sine of n pi over L times x, where n is 1, 2, 3, etc. Okay? So that's an example of taking a differential equation, putting it in a simpler form, identifying, guessing, and or taking an educated guess at the type of function which will solve it, and then using the boundary conditions to narrow it down. So we've got these solutions, these sinusoidal solutions. Now we continue solving this time-independent Schrodinger equation for the infinite square well. We talk about normalization, which we've mentioned before. So remember that the total probability of finding the particle in this well is 1. It has to be somewhere in there. So that means that the integral of the probability density, which is psi n star psi, must be equal to 1. Substituting for psi n, which is a sine of n pi x over L, and then we know the range here, in general, it's over all x, but we know that psi is 0 for x less than 0 and x greater than L, so that we run from 0 to L. So this becomes a squared times the integral from 0 to L of sine squared n pi x over L dx is equal to 1. You can look this up in integral tables, but the fastest way to do this is a sort of a nice nifty fact, is that the average value of sine squared over one oscillation is a half. So the integral from 0 to L, since it's the interval length is L and the average value is a half, the integral evaluates to L over 2. So we have a squared times L over 2 is equal to 1, or a squared is 2 over L, or a is equal to the square root of 2 over L. Okay, so that's an example of normalization, finding the constant which makes the integral of the probability density equal to 1. So we have our family of functions now. We know what a is. It's square root of 2 over L. And the wave functions are psi n is square root of 2 over L times sine of n pi x over L. What about the energies? We care a lot about energy is very important, determines the behavior of systems. So the discrete values of k, which are n pi over L for n, 1, 2, 3, and so forth, lead to discrete allowed values of energy, because our definition of k involves the energy. So if k can only take on certain allowed values, then E can only take on certain allowed values. So how does that work out? Well, these are both equal to k, so we can set n pi over L equal to the square root of 2me over h bar. Square both sides, so we get n squared pi squared over L squared is equal to 2me over h bar squared, and then solve for E. And we get E indexed by n, since it depends on n, is equal to n squared times pi squared, we bring up the h bar squared, and over 2m, which we divide by 2m here, 2ml squared, for n equal 1, 2, 3, and so forth. And that's actually equivalent to what we found before using the de Broglie wavelength, the rough treatment we found before. But we've gotten it now officially from a full-scale differential equation, so we can be more confident of our energies here. And this is just a pictorial representation. These are the first 3 wave functions: sine of pi x over L, which goes through half an oscillation; sine of 2 pi x over L, which goes through a whole oscillation; and sine of 3 pi x over L, which goes through 1.5 oscillations. And then psi squared, whereas psi can be negative, psi squared, since its probability, can't be negative. So when we square this, the negative parts become positive, and we get 1 hump or 2 humps or 3 humps. And the energy of these 3 would be, well, the energy E1 plugging in 1 here would be this pi squared h bar squared over 2ml squared. But then as n increases, when n becomes 2, n squared is 4, so it's just 4 times the original energy level E1. And then when n is 3, it's 9 times E1. So that would be these three, and then 16 and 25 and so forth. So the energy goes up as n squared, and it's quantized. So that's what we mean by, that's why we have this name quantum physics and quantum mechanics, because the energy can only take on certain allowed or quantized values. All right, what about the correspondence principle? Agreement with classical physics in the limit of large n, where n is this quantum number, so-called quantum number that we have. Remember Bohr, back at the Bohr atom, said that in the limits where classical and quantum theories should agree, the quantum theory must reduce to the classical result. Well, if we look at this system, classically, if we set up like a a big deep box, and we put a ball in it, and with very low friction and a very elastic ball, and roll the ball back and forth, the probability of finding the ball in any one place, since it would just be bouncing back and forth, would be equal. There would be no preferred position. And since the total probability should be 1, and the position has length L, the uniform or constant probability over the whole interval will be 1 over L. So it'd be because 1 over L times the length L would be 1. Quantum mechanically, as we've just looked at, solving this system quantum mechanically, we know that the probability density is the wave function squared, which is 2 over L times, because the normalization constant was square root of 2 over L, 2 over L times sine squared of knx, since, yeah, sine squared of knx. As I said before, the average value of sine squared over one cycle is a half. So therefore, over many cycles, this average value of sine squared is going to be a half, and multiplying a half, 1/2 times 2 over L, the 2's cancel, and we just get 1 over L, which agrees with the classical result of the uniform probability 1 over L. And furthermore, as n increases, we'll see more and more oscillations, more and more rapid oscillations, and so less variance in the probability of the wave function. So a closer and closer approach to a uniform probability spread across the entire space of the well. Okay, so just to summarize, one-dimensional square well is a very useful model system, and our first system that we've applied the Schrodinger equation to, we've seen the importance of boundary conditions and normalization, and how the boundary conditions lead to only certain allowed values for the wave number k, and through that the energy n. That's our quantization. So the boundary conditions lead to these certain quantized energy levels, and we've seen that the result follows the correspondence principle. So we can be confident that it is physically valid. Okay, thank you for your attention, and we'll work some problems on this in class.